Hi, everyone, and welcome to this next installment in my Algebra and Pre-Calculus series of videos. And this video, the topic is complex numbers. Now, this is something we haven't talked about yet. Up until this point, we've been talking about the real number system. And actually, in the very beginning, one of the first things we talked about, I think in my very first video in this playlist, was a description of the most common sets of numbers that we come across in mathematics. Now we had the natural numbers. Those were the positive whole numbers, like 1, 2, 3, dot, dot, dot. All right, so those were the natural numbers. Those are supposed to be set brackets. So let's say this is the set. Let me get rid of those brackets. Let's just use, you know what I mean, the set of natural numbers. 1, 2, 3, dot, dot, dot. Right? And then the natural numbers were inside of this larger set called the whole numbers. Now, the whole numbers also included the number 0. So every natural number is a whole number. Then you also have the number 0. Then the whole numbers are inside of this larger set called the integers. The integers are all the whole numbers that are positive and negative. All the counting numbers that are positive, negative, and 0. So with the whole numbers, we throw in the number 0, the integers, everything plus the negative numbers. Then we've got this larger set here. The integers are all part of this larger set called the rational numbers, and the rational numbers are all numbers that can be expressed as a fraction, including whole numbers, including 0, but including things like 2/3 or -17/5, anything that could be expressed as a fraction. And then separate from those rational numbers, everything that's not rational is called irrational. Let me write that a little bit neater. Irrational. So irrational numbers are like the square root of 2 or the square root of 11, square root of numbers that don't simplify. The square root of, it's not every square root. So for example, the square root of 4 is a natural number, right? Because that's square root of 4 equals 2. But irrational numbers, basically they're, to be technical, they're non-terminating, non-repeating decimals. Pi is over there, right? The number e is over there. And if we take all of this together, all of the rationals and all of the irrational numbers, that is the set of, not R-A, R-E-A-L-S, the real numbers, right? The real numbers is everything. Or so we've been saying. Up to this point, the real numbers have been all numbers. What we're going to talk about today is another set of numbers that actually is larger, that includes the real numbers and everything else. And these are called the complex numbers. So every natural number is a whole number. Every whole number is also an integer. Every integer is rational. Every rational is also real. Every real number is also complex. But there are some complex numbers that are not real numbers. So that's what we want to talk about today. Now, let's use something as a backdrop, something we've done before, we've used before, we've seen before, we've discussed before. Let's go with a quadratic. So here we have a quadratic function. Now we've talked in some of my previous videos about quadratic expressions, quadratic equations, quadratic graphs. Now we're talking about quadratic functions, but it's the same ax squared plus bx plus c. So in this case, f of x is equal to x squared minus 5x plus 5. Now let's say we wanted to find the zeros. Find the zeros of this function. Well, up to this point, if it had any, those zeros are synonymous with x-intercepts of the graph. But it doesn't always actually work that way when we talk about complex numbers, and we'll see why in a little bit. So a zero is any answer that you get. A zero is any answer that you get when you replace y with zero. That's why we call them zeros. You do zero instead of f of x. Remember, f of x is the same as y. Let's just write f of x and y are more or less interchangeable. Right, so 0 equals x squared minus 5x plus 6. Now this one is on the easier end of the spectrum. I only say that because we could actually factor this equation, or this expression on the right-hand side, the expression on the right. So we could say 0 is equal to, that would be x minus 3 and x minus 2. Right? Reverse foiling. Right? FOIL is when you multiply. Factoring is when you reverse the process of multiplication. If you're not sure how I got from this step to this step, go back in my playlist. I have a video on factoring, and it will be in there in detail. Okay, now we have also, again, something we've seen before. At this point in this series of videos, so much of what we're doing and going to be doing involves things we've seen before. So I'm going to, you're going to hear me saying, we've used this before, we've used that before. What I mean is, those things were explained in previous videos leading up to this one. So we have the zero factor theorem that says, okay, if two things multiply together, this is thing number one, and this is thing number two. If two things multiply together to give you 0, then either the first one has to be 0, so the x minus 3 has to be 0, or the second one has to be 0, so x minus 2 is equal to 0. So we actually get two answers here. If we add 3 to both sides, we'll get x is equal to 3. Okay, boom. Add 2 to both sides, we get x is equal to 2. Now what this means is, in terms of the graph of this function, there's an x-intercept when x is equal to 2. There's an x-intercept when x is equal to 3, and the graph, does something like this. Okay, we've also seen this in the context of the quadratic formula. Again, something I covered in a previous video, and that's an if-then statement. So if ax squared plus bx plus c is equal to 0, then x is equal to negative b. This is the quadratic formula, plus or minus the square root b squared minus 4ac, all divided by 2a. And this thing under the square root, we call that the discriminant. And the discriminant, and I'm not going to spend too much time on it because, again, this is something that I covered in a previous video. Well, this tells you how many solutions you have. If this is positive, then you're going to get a plus and a minus. And if this is a negative number, if b squared minus 4ac is negative, then you get a negative under the square root. In that case, no solutions. Well, no solutions if we're only talking about real numbers. Okay, so this has all been review of a handful of my previous videos. Now, we just looked at this guy right here, x squared minus 5x plus 6. Let's look at a slightly different quadratic function that's going to work when we try to do the same thing. It's going to play out a little bit differently. Okay, so let's go with g of x equals x squared minus 6x plus 10. It's a similar looking function, right? They're both quadratics. They both have a leading coefficient of 1. So we looked at this one first, now we look at this one, and it seems like, however, f of x sort of worked, g of x looks like it's the same type of problem, right? So with f of x, with the first one, let me get a, let's go with red. We got two answers here. X is equal to 2. And x is equal to 3. Well, let's look at g of x. Well, g of x, if you try to factor it, you'll quickly find out that this doesn't factor. So when the quadratic expression doesn't factor, we could use the quadratic formula. So x is equal to, let's just make sure we specify so everyone is on the same page. Our a is equal to 1, right? 1x squared. Our b is equal to -6, and our c is equal to 10. I'm talking about the a, the b, and the c in the ax squared plus bx plus c definition of quadratic expressions, right? So the coefficients and the constant at the end, the 1, the -6, and the 10. So the quadratic formula is telling us that x is equal to negative b, so negative of a -6, which is a +6, negative b plus or minus, because there could be up to 2 answers, plus or minus the square root of b squared. That's -6 squared. That's -6 times -6, which is 36, minus 4 times a, which is 1, times c, which is 10. So I'm just taking the a, the b, and the c, plugging these 3 numbers into the quadratic formula, all divided by 2 times a, so 2 times 1. Okay. So let's simplify if we can. That's 6 plus or minus, well, what's going on under the square root? We could simplify that. So that's 36 minus 4 times 1 is 4 times 10 is 40, so 36 minus 40, all divided by 2. So still looking under the square root, that's 6 plus or minus the square root. 36 minus 40 gives us a -4. All over 2. And then what do we say at this point? We say no solution, because you cannot take the square root of a negative number. Okay, well, now with complex numbers, we say, wait a second, hold on. What if you could? What if you could take the square root of -4? What would that have to look like? Well, we have to introduce a new symbol and a new topic or new concept. And it's a type of number unlike any of the numbers that we've been working with so far. We're going to call this number the imaginary number, because it doesn't exist in the physical world in the sense that numbers, in the sense that the way we normally look at numbers in terms of amounts or values or distances, we'll call the imaginary number we'll call it I for imaginary. And I is going to equal something that up until this point we've been saying doesn't exist. I is equal to the square root of -1. Okay, this is important. This is something we're going to be using quite a bit moving forward. All right, we're saying, okay, normally, yes. Normally, if you see this, what I just highlighted in yellow, normally if you see that, you say, okay, that doesn't exist, no solution. But what we're saying, when we say no solution, the implication there is there is no solution. There's a word in between there, no real number solution. There is no real number that is a solution to this original equation. Right, so we're solving this guy right here. 0 equals x squared minus 6x plus 10. This has no real number solution. But if we consider these imaginary numbers, and it's all based off of the square root of -1, then this allows us to solve this equation. Now, it's not going to give us a number in the sense, like, if you're thinking real numbers, it's still not going to give us a real number solution. The solution is going to contain the imaginary number I. Okay, so the imaginary number I is a symbol that stands for the square root of -1. And so these complex numbers, now this is definition, I'll write it in a different color. The complex numbers are numbers that look like this: a plus b times I. A plus b times I, where the a and b are real numbers. So the a, we call this the real part. And the bi, we call this the imaginary part. And together, that is one complex number. So for example, what does a complex number look like? Well, 2 plus 3i, that's a complex number. -4 plus 26i, that's a complex number. 4i, that's a complex number, because the real part, even though there's nothing written there, we could say, okay, there's a 0 plus. We could say 0 plus 4i. That's a complex number. 6, that's a real number. 6 is a real number. It's also a complex number, because we could write 6 as 6 plus 0i. These are all complex numbers. Every real number is also a complex number. So we're going to be using complex numbers. I'm going to use this in this context as solutions to equations. That's going to happen in my next video, the one immediately following this one. We're going to be talking about more solving quadratic equations. I might finish up this video on one of these problems, but before that, we have to talk about the things, the basic operations that we're all familiar with in our number system, the real numbers. We know how to add, right? We know how to subtract, multiply, we know how to divide. So let's just make sure we're understanding how to do those things with complex numbers. It turns out it's going to be pretty straightforward, because there's going to be so many similarities with things that we already know how to do, or at least we've already covered. Hopefully we already know how to do. So number one, no, let me come back to this one. Oh, no, wait, this is the one we already did, right? Yeah, this is the one we already did. Okay, so number one, perform the indicated operation. So the indicated operation here is subtraction of two numbers, right? Subtraction of two numbers. This is a complex number, 2 plus 3i. This is another complex number, 8 minus 3i. right? So we're subtracting two complex numbers. Now, anytime you're either adding, subtracting, multiplying, or dividing complex numbers, your final answer should look like a complex number, a plus bi. The a and the b are real numbers, and I is that imaginary square root of -1. But instead of writing the square root of -1, we just use the symbol I. Okay, so my first question is, how would you do this problem over here on the right? 2 plus 3x minus 8 minus 3x. How would you do that? Well, this is something hopefully we've seen many, many times leading up to this video. Combine like terms. Numbers go with numbers, x's go with x's. We have the distributive law. So we would have to distribute this minus signs. We're minusing an 8. We're minusing a minus 3x. So we would have 2 plus 3x. That first set of parentheses, the parentheses aren't really doing anything. In the second set, we're getting rid of by distributing the minus. So that's a minus 8. And minus a minus is a plus 3x. So the 2 and the -8, the 2 and the -8 combine to be a -6. And the 3x plus 3x is 6x. So we could write it like this, or we could say 6x. We could put the 6x first since it's positive, 6x minus 6. Either way. Okay, that is a review of something in the distant past. Well, we solved this problem in the exact same way. Collect like terms, numbers, real part goes with real part. Imaginary part goes with imaginary part, and you treat that I just like you treat any other variable. So you distribute the minus sign. And notice, as I'm writing this out, 2 plus 3i minus 8 plus 3i. It's exactly, with it really, the only difference is there's an I in place of an X. But 2 and -8 gives you a -6. 3i plus 3i is 6i. Or you could write 6i minus 6. So notice it's looking identical. Now, the only difference is the standard form. We generally put the I second. So we wouldn't write it like this. We would write it like this. The -6 is the real part because it doesn't have an I. And the 6i is the imaginary part. And together, this is one complex number. This is one single complex number. Complex numbers have two parts, a real part and an imaginary part. Okay, so how do you add and subtract complex numbers? The same way you add and subtract binomials. Combine like terms, distribute negative signs, distribute multiplication, no differences. Okay, number 2, multiplication. Well, you would solve this problem. You would actually do this multiplication in exactly the same way you would if it looked like something that you've previously seen. A binomial times a binomial, 2 minus 5x times 7 minus 4x. How would we do this? Well, we would FOIL. Right? That's one way to remember that there's 4 steps here. First times first, outer times outer, inner times inner, last times last. We would multiply everything out. So we're going to do the exact same thing. So let's see how this works. It should be very familiar. So let's just, let me put the word FOIL back there. First times first. 2 times 7. That's the F. Outer times outer. So we got 2 times a minus 4i. So that's 2 times 4 is 8. There's a minus sign. There's an I. So that's minus 8i. The I in FOIL is inner times inner. 7 times 5 is 35. There's a 1 negative, 1 positive. So that's minus 35i. And then last times last. The L in FOIL. So minus 5 times a minus 4 is a positive 20. And just like x times x is x squared, I times I is I squared. T times T is T squared. M times M is M squared. Anything times itself means squared. So that would be plus 20 I squared. So no surprises yet. Nothing is different. Had this been an X instead of an I, combine like terms, right? We've got 14, a minus 8 and a minus 35. That gives us a total of what? Minus 43 I's plus. Okay, so now here is the first difference. The first difference we see, and I say different from what we would do if that I was just an X. If that I was an X, everything we've done so far has been something similar to what we've already done. So now what do we do with I squared? What do we do with I squared? Well, on the previous handful of slides, I said, okay, we're going to be working with this new symbol I, and that symbol I is holding the place of the square root of -1. Well, what happens if you square both sides of this equation? So what happens if you do that? Square both sides. You get I squared on the left, and the square root will cancel. So you've got -1. I squared, because I is equal to the square root of -1, I squared should be equal to -1. Now, at this point, if you're wondering, like, what does I look like? Where does I exist in the physical world? We use this I conceptually. We definitely do in the physical world. But unless you're familiar with one of those, one of those specific scenarios, like if you have a background in the physics of electricity, you'll see I all over the place. But in the context of like a pre-calculus course, what does I look like in terms of things that we already know, that we've already covered? Well, it doesn't. We can't draw a line with the length I. Right? Nothing weighs I pounds. There's no such thing as I dollars or I minutes. We can't use it to measure something tangible in the same way, in the same linear way that we do with the real numbers. We're going to get to that. We're going to get to that. At this point, we're starting from the beginning. We're laying a foundation. Add, subtract, multiply, divide, and then we'll go from there. So at this point, I is the square root of -1, or I squared is equal to -1. So this would be 14 minus 43i. Those two numbers don't combine, right? In the same way that 14 minus 43x, we wouldn't combine the 14 and the 43 if one of those numbers had an x. Okay, plus, oh, I'm writing it again. I don't need to write it again. Plus 20 times -1. Now, I'm taking a lot longer to do this problem than it really needs. This is a relatively short problem, but I'm explaining as I go, so it's going to take a little bit longer. So this is a real number, 14. This is also a real number. So we have two real numbers that we could combine. We've got a 14, and I'll put this 20 second, and that's actually going to be a minus 20 because it's plus 20 times -1. So minus 20, and then a minus 43i. 14 minus 20, we could put those two guys together. That's -6 minus 43i. And our final answer should always be in the form something plus something I, where those two somethings, those are real numbers. The A and the B are real numbers. Okay, we looked at subtraction. We looked at multiplication. Now we have division. We have division. We have a complex number divided by a complex number. You look at the top, you see 8i. You say, oh, well, that's just the imaginary part. Well, that's actually 0 plus 8i on top, 9 minus 2i on the bottom. So we have a complex number on the top. We have a complex number on the bottom. Now, the way to divide two complex numbers, we have to use something that we've seen before. We just have to use it now in a different context, the conjugate. This problem is going to be a model for any problem where you have a division, we have a fraction of complex numbers. Only if, no, you know what? I was going to say only if the A on the bottom is not 0, but this method works no matter what. This method always works. Okay, so we have to multiply by the conjugate. And just a review, the conjugate of a binomial. The conjugate of, I'll say, I don't want to use A and B because we've been using A and B. I'll say the conjugate of M plus N, where M and N could be anything. M is something, N is something else. They're connected with a plus sign. The conjugate of something plus something is, we just change the plus to a minus, is M minus N. That's it. The conjugate of N minus N is M plus N. And so we want to multiply by the conjugate of the denominator. We saw this previously. This is going way back to maybe the third video in this playlist, where we simplified expressions where you had square roots in the denominator of a fraction. We use the conjugate in that context, so we're going to use the conjugate in the exact same way. We use it to eliminate square roots in the denominator. Well, I is a square root. It is the square root of -1. So we're going to use the conjugate we're using it in the same way that we've seen it before to get rid of or to eliminate square roots. There's a square root right there in the denominator of a fraction. So we'll multiply 9 plus 2i, conjugate of the denominator. And whatever we do to the bottom, we got to balance that off by doing the same thing to the top. Okay, and if you do this, it will cancel out the I on the bottom 100% of the time. All right, so let me rewrite this so we have a little bit more room down here. We've got 8I multiplied by 9 plus 2I. And then on the bottom, we've got 9 minus 2I multiplied also by 9 plus 2I. Okay, on the top, we're going to distribute because there's only one factor on the outside. On the bottom, we've got 2 terms times 2 terms, so we have to FOIL on the bottom. Okay, so slightly different approach to multiplication on the top versus the bottom. So on the top, if we multiply through 8I times 9, 8I times 9, looking right here. 9 times 8 is 72, and there's an I, so that's 72I. And then 8I times 2I. 8I times 2I would be 16. That's the 8 times 2. And then I times I is I squared. So that's the top. We haven't canceled off the I. That's not our goal here. We can't just cancel it off. Our goal is to only cancel out the I on the bottom in the denominator. Okay, so now let's go down to the bottom. F, FOIL. First times first, that's 9 times 9. O, outer. Oop, didn't want to go forward yet. O for outer, outer times outer. So that's 9 times 2I, outer times outer. So that's plus 18I. And then I for inner times inner. So that's negative 2I times 9. So that gives us, well, now we have one positive, one negative. So that's a minus 18I. And then last times last, the L in FOIL, last times last, negative 2I times positive 2I. Negative times a positive is a negative. 2 times 2 is 4. I times I is I squared. Now, the whole point of using the conjugate, I don't want to just say, remember to use the conjugate. Well, why? Every time we use the conjugate, the outer times outer and the inner times inner will always do this. One positive, one negative, same number. They add up to 0. And if you're using the conjugate, the plus, didn't want to do that. I wanted a red pen. The outer times outer will be one sign, either positive or negative, and the inner times inner will be the same number, but the opposite sign. So they will always cancel, and that's the whole point of the conjugate. Now, let me switch my highlighter to a different color. Well, let's go with green. We got an I squared there. We got an I squared there. Don't forget I squared. And this is a new symbol that we're using, but I squared. Okay, there we go. Is equal to -1, and this I squared is equal to -1. So what do we got? On top, we've got 72I plus 16 times -1. On the bottom, we've got 81 minus 4 times -1. Ooh, there we go. Right, those I squares became, I'll just stick with my color coding, those I squares became -1s. Right? The I stays I. Right? I is a symbol. It means the square root of -1. But we're just treating it like any other variable, except when we square it, it actually becomes a real number. Okay, so that's 72i on top, the numerator of the fraction. We got 72i plus 16 times -1, so that's minus 16. It keeps it go. Jump into the next slide. Okay, and on the bottom, we've got 81 minus a -4. 4 times -1 is a -4, so minus a minus is a plus. So that's plus 4. +81 plus 4 is 85. And on top, we've got 72i minus 16. All right, so we're basically done, but if we want to, and I'm going back to the original problem, if we want to write the result in standard form, so a real number plus a real number times I, we could just take this answer. So I'm gonna go ahead and give this a dotted circle, maybe not like a full green circle, but I'll say like that's basically our answer. It's just not in the right form. We want to put the 16 first, the 72 second, and split it up into two parts. The real part separate from the imaginary part. So we've got 72i over 85, that's one number. We've got a -16 over 85, that's another number. So we could split it up and put the real part first. -16 over 85. I don't know why. I apologize. I don't know why it keeps jumping to the next slide. -16 over 85. And then the 72 is positive, so we'll say plus 72 over 85 times I. Right, just make sure you're clear on how I jumped from that second to last step to the last step. All we're doing is sort of uncombining the fractions with the common denominator and then putting the number with the I second and the number without the I first. Okay, so that would be our final answer. The A is the fraction -16 over 85. The B is the fraction 72 over 85. Okay, so we've done, let's see, we did subtraction, then we did multiplication, then we did division. Let's see, next problem. Well, what does this new concept, this new object that we can now work with, this I with the square root of -1, it allows us to work with things that we've previously been calling, does not exist. The square root of -36 does not exist because it's a negative number. Well, again, it doesn't exist in the real numbers because it is not a real number. But we've seen some properties of radicals before. So one of them is, let's write them over here in the bottom right corner, the square root of something times something. So the square root of a times b. I'm not going to use a and b. I'm going to use x and y. So we're using a and b already up here in the problem. The square root of x times y is equal to the square root of the first times the square root of the second. Okay, well, let's apply that to this problem. We could split up the square root. So that's 5 times the square root of 36. And let's just break off that negative sign and split it up as the -36 as 36, positive 36 times negative 1. And we could do the same thing to the negative 81. We could say that that's 81 times the negative 1. So we've got plus 7 times the square root of 81 times the square root of negative 1. Well, the square root of 36, we're good with that. That's positive. That's a square root of a positive number. So the square root of 36 is 6. And the square root of 81 is 9. So that is 5 times 6 times, and now the square root of negative 1, we're calling this I. So 5 times 6 times I. And then for the 7 times the square root of 81 times the square root of negative 1, that's 7 times 9 times I. And we're getting close here. We're almost done. 5 times 6 is 30 times I, so that's 30I. 7 times 9 is 63 times I, so that's 63I. And that will give us a total of 93 times I. Now, most likely you've been working with real numbers your entire life since you were 2 years old and you started learning the number systems. Probably started with counting 1, 2, 3, 4, 5. Then you learned about zeros and negative numbers. And then later on in life, you started learning about fractions and decimals and square roots and things like that, exponents. So with the real number system, you've been working with those for your entire life. If you've never seen complex numbers before, don't expect to understand complex numbers inside and out just from one video. Right? This is an extension to the number system, but this is sort of a new number system. So we're just getting started with complex numbers. Okay, last question. What are we using complex numbers for in the context of, let's say, a pre-calculus class? Actually, we have 2 questions left. Let's do this one quick, and then we'll move on to the next one, which is solving using the quadratic formula. And that'll be the last one we do. But let's do this problem, which is similar to what we've done so far. And we've got, let me use my highlighter here. We've got a negative 5 on top, and that's being divided by 40. Let me switch here to, so much switching. Okay, so that's negative 5 divided by 40. And then we've also got this square root of negative 32, and that's also being divided by 40. And they're connected with a minus sign. Right, so we're basically just splitting up this fraction into 2 parts. Then we've got the square root of negative 32, which is also being divided by 40. Okay, so let me get rid of all that highlighting. We're just taking the 2 terms in the numerator. They're both divided by 40, so we could split it up into 2 fractions. Each fraction has a 40 in the denominator. Okay, so negative 5 over 40, we could reduce that fraction, because 40 is 5 times 8. So that will reduce to negative 1 over 8. And then we've got a minus sign. Well, there's a few different paths we could take to get through the details of simplifying. But this is just one that makes sense, to me. The square root of Negative 32, we'll do the same thing we just did. We'll break it up as the square root of 32 times the square root of negative 1. And the square root of 32, well, what is that? That should be 4 times the square root of 2. Square root of 32 is 4 times the square root of 2. And then the square root of negative 1 is I. So just to make sure everyone's on the same page, how did I get from here to here? The square root of 32, well, 32 contains a perfect square. That's 16 times 2. So that's the square root of 16 times the square root of 2, and the square root of 16, that's a perfect square. So that's 4 times the square root of 2. So that's where that square root of 32 becoming this 4 square root of 2, that's where that came from. And then we've got an I. And now we got a 4 on top, a 40 on the bottom. They're both divisible by 4. So we could do some canceling there. So this is negative 1 over 8 minus, let's see, I'll use red to do a little bit of marking here. The 4 and the 40 become a 1 and a 10. Because we canceled a 4 from each of those. And it looks like on top we've got the square root of 2 times I, and on the bottom we've got the number 10. And there's our answer. We just tend to put the I separate from the number in front. So we could say negative 1 over 8 minus the square root of 2 over 10 times I. I mean, everything we've done in these 5 problems would be identical if you just replaced the I with an X, with the one exception of that if you square an I, you get a -1. So there's some sort of new new stuff going on here, but a lot of it is we're recycling things that we've done in the past. Okay, so last one, and now this is like going back to the very first slide where I did a couple of quadratic equations. So here's another quadratic equation. We have the quadratic formula. It's an if-then statement. If you have an equation of the form ax squared, in this case a is 1, plus bx, so here the b is the -4, plus c, so c would be the 29. If you have an equation of this form, then your answer, or answers, plural, would be x is equal to quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So to use the quadratic formula, you're taking the a, the b, and the c from your problem. Again, this is something we've done. I'm going somewhat quickly because this is something we've done in previous videos where I actually explain this slowly. So negative b, negative of a -4 would be +4, plus or minus the square root of b squared. So that's -4 times itself, which would be +16, minus 4 times a times c. So that's 29, all divided by 2 times a, and a is 1. Okay, so now we just have to simplify. We have to simplify. So let's see, we've got 4 on the outside, and we've got plus or minus, because two answers, the square root of 16 minus, well, if we take 4 times 1, that's 4, and 4 times 29 is actually 116. And on the bottom, we've got 2 times 1, which is 2. So under the square root, we've got a negative number. 16 minus 116 is negative 100. Negative 100. So we've got 4 plus or minus the square root. Negative 100 all divided by 2. And so anytime you see a negative number under the square roots, now you have to be careful of the context. In a math class, sometimes you're allowed to consider complex numbers. You're allowed to use them. And other times, you're restricted to only using real numbers. You have to just pay attention to the directions in the problem or what's currently going on in the course. But if you're allowed to use complex numbers, then anytime you see a negative sign under a square root, just take it out. So instead of the square root of negative 100, we have the square root of positive 100. Just take it out and make it separate, times the square root of negative 1. I'm going to come over here so I have a little bit more room. So that's 4 plus or minus. The square root of 100 is 10. The square root of negative 1 is what we are calling I. All divided by 2. And now we are very close to being done simplifying. We can do a little bit more. Split this up into 2 separate fractions. We've got 4 over 2 plus or minus 10i over 2 let's see, that's 10i over 2. 4 over 2 is 2. 10 over 2 is 5. So we can write that as 2 plus or minus 5i. 2 plus or minus 5i. So that's one way of writing the answer. That's 2 answers right there. That's 2 complex numbers. Those 2 complex numbers. So let me just put the word or here, because you could write it one way or the other. You could say 2 plus or minus 5i, or you could write that answer as 2 plus 5i and 2 minus 5i. You can write them separate. Either way, you have 2 answers, 2 complex numbers. Now, with quadratics, with the x to the second power, if you're only allowed to use real numbers, sometimes you have no solution, sometimes you have 1 solution, sometimes you have 2 solutions. That's what the discriminant tells us. But if you're allowed complex numbers, then any quadratic always has 2 answers. It might be the same number repeated twice, but you always have 2 answers. Okay, that does it for this foundational introduction to complex numbers. It's not something you should be 100% comfortable with, especially the meaning of the I or the square root of negative 1. But we'll talk more about the complex numbers and use them more in the next video, which will be a continuation of this one. All right, that's it for now. Hope this was helpful.